Today we are going to discuss about RL, RC and RLC parallel circuits. So I will first take the case of my RL circuit. So I will take here RL parallel circuit. So let me draw that parallel circuit. In place of the voltage source, I said that okay, voltage source हम वही रखते हैं, V रख लेते हैं, for example, but I will use currents. So I will take here a resistance and an inductor which are both parallel to my voltage source. Like this. So let this be the resistance R and this be the inductor L. Let this be the total current flowing through it is I, and let these currents be, two currents will be there, let this be IR and this be I. These are the simple notations. You may use another notations also, right? So now instead of the impedance set, as I said, I will make use of admittance. Impedance is Z, but I will make use of admittance here. And what is the relation between admittance and impedance? Y. Then can I say that Z is equal to 1 by Y? Why we do it? Because it is easy to take admittances in parallel. Because if, for example, if this is the R and the admittance by this resistor is YR and the admittance of this is YL, then definitely I will say the combined admittance will be the sum of this with some addition of G operator along with the YL. I will show you how I will do that. So I will assume here the current, total current I. So definitely this total current I must be equal to the IL plus IR. Right. Now what is I? If I assume or if I take this circuit like this, that this is my voltage source and this combined impedance is Z or admittance is Y. Z. For example, here I'm taking only the case of one impedance Z. So this combined, that is combination of R and L in parallel, will have an impedance. I've named that Z. So can I say that if this is my voltage source and this is I, from here can I say my I is equal to V by Z? Simple Ohm's law. Instead of R I'm using here Z. This should be equal to, if I take IR first, so IR is nothing but the voltage divided by the resistance. This is what I have, because if this is the voltage, definitely at this point my voltage is V, because there is no component in between these 2 points. So this is V. It means definitely IR, it is equal to V by R, right? Plus, what is IL? If I take IL, what is IL? IL is the current flowing through the inductor L. So definitely IL will be equal to the voltage divided by the impedance. That is, you know, the impedance of an inductor is XL. But we have studied that whenever we are discussing only single inductor, there is a phase difference between the voltage and the current, and that phase difference is equal to plus 90 degree or minus 90 degree. Can anybody tell me? In the case of inductor, our voltage leads but current lags the voltage source. It means whenever we are considering the current, it should be minus 90 degree, because yeah, so it is minus 90 degree. Now the same can be represented as, look here, the V is constant in everywhere. Instead of this angle of minus 90 degree, can I use minus J? We have studied this J concept. It means whenever we have a phase shift of 90 degree, I will make use of J operator, but this 90 is in minus, or I will say it is in the clockwise direction. This is the scenario. This is my current over here. Sorry, this should be my voltage. This is my voltage over here, and this is my current. It means here my current is lagging the voltage by angle of 90 degree if only I am considering my inductor. अगर सिर्फ इंडक्टर की हम बात करें, so it means I am moving in the opposite direction or in the clockwise direction. For the clockwise we have minus, and there is a phase shift to 90 degree. It means I will have J. So I will write here minus of J, right? Now in the parallel circuits, instead of 1 by Z, we use Y, comma, instead of 1 by R, we use G, that is conductance, and in place of 1 by XL, we use BL. And in the next topic, we are going to use 1 by xc. So I will write here it is equal to pc. So this is the simple notations that I will use. So from these notations, can I say my v by z can be represented as v into y? This can be represented like this because of 1 by z is equal to y. Similarly, it is equal to v into g. Okay, now I will adjust my minus j, so it will be minus j v by xl. 1 by xl is written as v. I can take v outside and it will be cancelled. So I will say my admittance y is equal to g minus j of vl. So this is the one way of representing my parallel circuits. In the parallel, I make use of admittances, and instead of my resistance, I use conductance. Instead of XL, I use VL. Is it clear? Now, this is important. Whenever I have been asked that what is my admittance, or if I have been asked the impedance, then I will simply say that whatever the value I have obtained, so take the inverse of that as z is equal to 1 by y. So this is equal to 1 by g minus j of VL. So this will be my impedance. So you can convert it later into any term once you have solved the circuitry. Most important is to solve it. So it is better to solve all these in admittances. That's why I have used these notations, right? Similarly, if I take this current, so can I say, okay, let me draw the triangle first so that it will be easy for you. So if I say here, now, if this is my current I current, let it be IR, not I, because I have used I for, let me small I, we use this small I. So let this be IR, because we know that voltage and current have the same phase in the case of the resistance. So I said that IR will be definitely at the same phase as that of V. So I have taken this reference IR. Then definitely IL, which is lagging the voltage by 90 degrees. So it is like this. So in this case, my IL will be equal to, you can write here, V times of VL. This is what we have obtained. VBL and minus J is accommodated over here in the direction. That is, I have taken it in the downward direction, and it is current, so it is lagging. So it is minus 90 degrees. So this is accommodated here in this phasor diagram. Then definitely the resultant of it will be this one. What is the resultant? Is the total current I, and this total current is equal to V into Y. So definitely you will find a angle theta, which is in the clockwise direction. It means in this scenario, or in the parallel circuit, RL parallel circuit, your current will lag. Your current is lagging here with an angle theta, and this theta will be represented in, if I'm talking here in terms of the currents, it will be tangent inverse of, you know what is tangent. Again, I will make use of this Pandit Badri Prasad Har Bole. You all know how to remember this. So this is my tangent. So it is perpendicular upon base. So what is perpendicular to theta? It is IL divided by what is base? IR. Now, is it right or something is left here? Something is left. What it is? I have only taken the magnitude over here. What about the direction? Phasor is also giving me the direction. So it is saying it is downward. It means it should be minus of IL. So this will be my theta in the case of my current triangle. Current triangle. We have done this, all these things in the case of RL, RC and RLC series circuits, but now we have just changed our notations for the parallel circuits. We have switched from impedance to the admittance. Similarly, if I have to take the impedance triangle, then definitely for the resistance, in place of the resistance, I will use here conductance G. In place of inductance, if you remember, in the series RL, RC, RL circuit, the inductance IL was in this direction. ऐसा ऊपर की तरफ को होती थी वो, याद है किसी को? But in the parallel case, here the current is lagging, so we will have here this direction, and it is in the case of parallel circuit, we will make use of PL instead of XL. Then we have this resultant, which is definitely Y. So Y triangle is, it is in admittance triangle. This angle is theta. And you can have one more notation that Y is equal to under root of So I talk only in the terms of the magnitude, it is G square plus BL square. Similarly, over here you can say that I is equal to under root of IR square plus IL square. This is simple Pythagoras theorem. You can obtain this thing. As this is of 90 degree, you can obtain all these parameters. Similarly, over here theta will be equal to tangent inverse of minus BL upon G. And last one is the power triangle. I will write here, this is impedance triangle. Oh, sorry, not impedance. Now in this case, I will name it as admittance triangle because I have used here the admittance. Admittance triangle. The next one is the power triangle. What is power triangle? It is in terms of the power. You know, we have three types of powers. So I will draw directly over here. This is V square G. This is normally denoted as P. Then we have V square BL, that is denoted by QL. And last one is simply V square Y, which is denoted by S of the parent. S is equal to V square Y. So over here also you can find theta is equal to tangent inverse of QL upon P. Or in some of the books you will find it equal to PR because it is corresponding to the resistance. Right? Is it clear to you? Any doubts related to the RL parallel circuit? We have only switched to the current values and the admittance values. And we have to just remember that whenever there is a phase shift of 90 degree, we can replace it with the J. If it is in the plus 90 degree, we will replace it with plus J. If it is in the minus 90 degree, we will replace it with the minus J. Right. So now next I'm going to discuss about the RC parallel circuit. Second is RC, just a minute. RC parallel circuit. So it will be exactly similar to this RL parallel, only here the current will lead the voltage by 90 degree. So let's see what's going to happen. First, draw the diagram of the circuit. So we have again assumed this voltage source, and R and C are connected in parallel to each other to this voltage source. This is C, this is R, but we have our same. Okay, the current I and yeah, yes. So I will assume again the current, total current I. It is taking here in the resistance and the capacitance balance. So I will name it as IR and IC. The admittance of this is YR, the admittance of this is YC. YC will be, okay, we will write it later. So this is my diagram. Now I don't need to find here the voltage because whatever the voltage is there between these 2 points will exist for these further 2 points across the resistor and further 2 points across the capacitor. So it means it will remain the same in parallel. So let's again do the same thing. That is, first we start with the current. So we will say I is equal to IR plus IC. You can convert in terms of the voltages. Again, we can assume this combined. I will now draw here only. I will assume that these two combined admittance is equal to Y. So I will write here in place of I as V by, directly I will write now, not in terms of Z, I will write it V into Y. It is equal to V into G, and there is a phase shift of current with respect to the voltage. As it is a capacitor, so the current leads here the voltage. It means definitely there will be a phase shift of plus 90 degree. So for the plus 90 degree, I will use plus J V into BC. Or simply I can write the combined admittance is equal to Y is equal to G plus J of BC. Right? Is it clear why I have used BC? I have just skipped one step. That step is, step, so it is V by Z. It is equal to, what is the impedance for the R? It is simply R, so I will write V by R. What is the impedance of the capacitor? It is XC, so I will write V by XC, but there is a phase shift of plus 90 degrees. So this phase shift was accompanied with the G operator. So we got this y is equal to G plus J of BC. Now, if I come back to all these three triangles, that is my current, impedance or admittance, I must say here, and the power triangle. So now the only difference will be here is that in place of this IL, I will have IC. In place of BL, I will have BC, and in place of QL, I will have QC. And these all are leading the voltage, conductance, or the power P. It means they will be in the positive side, and rest of the things will remain the same. So if I draw this current triangle, so in the current triangle, I will have, I can write that I is equal to under root of IR square plus IC square, right? And if I draw this, so I will take again IR as my reference. The reason is because in the resistance we have no phase difference between voltage and current, so definitely this is my IR. So definitely the IC will be phase shifted by 90 degree. So this will be plus 90 degree. That's why I have drawn it on the positive side, and the resultant of this, which is I, and this is my theta. Now you can see this theta automatically comes in the anti-clockwise direction or in the positive direction. So from here you can say that theta is equal to tangent inverse of, again the same formula. I will not write again how to write this tangent thing. So it is IC by IR, and it is in the positive side, so I will not use here minus. Then second one is my impedance triangle, or I will write here admittance. So in the admittance we have Z, in place of R I will use G. So again G is this one. Then we have in place of XC I will use BC. XC नेगेटिव साइड होता था, लेकिन BC कहाँ आएगा? पॉजिटिव साइड. सो इट मीन्स जो आपका फेजर बनेगा BC का, वो ये बनेगा. क्यों आ रहा है ये डिफरेंस? क्योंकि यहाँ पर हम करंट कैलकुलेट कर रहे हैं, वहां पर हम वोल्टेज कैलकुलेट करते थे. हम कहते थे वोल्टेज सीरीज में लैग करेगा तो वो नीचे की तरफ को आएगा, लेकिन करंट जो है वो हमारा लीड करता है वोल्टेज को इन द केस ऑफ कैपेसिटर. तो ऑटोमेटिकली यहाँ पे जब हम करंट्स में कैलकुलेशन करेंगे तो हमारा कैपेसिटर केस में BC पॉजिटिव साइड आ जाएगा. एंड द रिजल्टेंट ऑफ दिस इज डिनोटेड बाय Y. So we have Y here. This angle is theta. The rest of the things will be all same. सब जगह यही रहेंगे theta. Okay, I have denoted it. ऐसा Q नहीं है, ये theta है, इसको कंफ्यूज ना करें. So this is theta is equal to tangent inverse of, you can write here BC by G, or you can write here that Y is equal to under root of G square plus BC. Right? Similarly, you can do it for the third one is for the triangle, power triangle. Power triangle, again we will take the power of the across the resistance as V square G equal to P. Then the power across the capacitor, it is denoted by V square into BC, which is equal to, इससे नोट करते हैं QC से, and final of the total power noted by B square into Y, which is S theta. So over here we have theta is equal to tangent inverse of QC by P, where I can write that S is equal to under root of P square plus QC. Is it clear? So once we came to know about this RL and the RC parallel circuit, where we have seen that RL, in the RL parallel circuit, we have this IL. You can see here this IL, it is towards negative side, this BL towards negative side, and QL again towards the negative side, because it is here it is lagging. Whereas in the RC, the current is leading. So we have here IC positive, BC positive, and QC positive. It means if I have all or both this inductor and the capacitor, definitely one will go in the positive side, that is the due to the capacitance, and the other will go in the negative side due to the inductance. So the resultant of these two will be result into either the positive side or the negative side depending upon the values. So we'll see now how this RLC parallel circuit will be there. So next I will take the case of RLC parallel circuit. So in the parallel circuit, I will take these three in parallel to the voltage source. First one is this resistance. Then we have an inductor. And last one is the capacitor. Now let us take again this voltage source V, current, total current is I. This I will be divided across three branches named here as IR, IL and IC. Right? The admittance of this will be denoted as G. The admittance of this in place of Y I will write here BL, and for this will be BC. So how we'll solve it? Again the same concept, that KVL लगा देते हैं, KCL लगा देते हैं. We apply KCL as we have done in the rest of this one, or simply at this node if I find the total incoming current and total outgoing current, I will get that I will be equal to IR plus IL plus of IC. Now what is I? Again I can assume this combined circuit, this combined three impedances as Z or the admittance as Y. It can be denoted either by Z or Y, where Z is equal to 1 by Y. So we will get here I is simply the voltage divided by the combined impedance. So it will be V by Z. What is IR? It is the voltage divided by the resistance. What is resistance? It is R plus voltage. Voltage is same. They are all in parallel because divided by the impedance. What is impedance of this? It is noted as XL. And the capacitor case में XC. So it is Y by XL, V by XL. What is the phase difference between these two? In the case of the inductor, the current lead or lag the voltage. Current lag the voltage, so I will here minus 90 because I am finding IL. So it means current is lagging the voltage. That's why I have used it minus 90. Plus V by XC, but in the case of the capacitor, the current lead the voltage, so I will use here plus 90. Simple. Then you may convert these all impedance values into admittances. You will get V into Y, which is equal to V into G plus V into PL. What is for minus 90? We all know aware of it. It is minus J plus V into BC. For plus 90 it is plus J. I will cancel all these V values because they are common. So you will get here Y is equal to G plus, if I take J common outside, plus value is BC and the minus value is BL. So it is J minus J of BC minus BL. So this will be my combined admittance in the case of RLC parallel circuit. So now if I draw the phasor diagram, again remember the case of the RLC series circuit. In that case, what was my phasor? In that I have taken the voltage across the resistor as reference. Here I will take the current across the resistor as reference. So in my phasor diagram, I go down with, so I will make use of this. For example, let us assume this is my voltage, and definitely the current IR will be in the same direction. So I will use here IR. Right? I have given you the idea that why I always use this IR to be this one lesser than this voltage, because IR is the current flowing through the resistor, where V is the voltage across these 2 points or across the resistor. So definitely IR value is equal to V by R, which is smaller than the voltage V. So that's why this arrow is before this voltage V. Then next is one is in the positive direction. What is the positive direction current? It is IC current. So if I take, just a minute. So if I take the positive side, so we will have here IC if I take the negative side, I will have here the I. Oh, sorry, let me use this small I and small IC, and this is my I. But now both are in opposite direction. It means definitely we have to take the resultant of these two. You can take the resultant either in the positive direction or in the negative direction. I will assume it in the positive direction such that IC is greater than IL. It means this will be my difference of IC minus IL. So I will use only this part. Then the resultant will be in the positive side and it will be this current I. And the theta angle is in the anti-clockwise direction, means the combined RLC parallel circuit, we have current, this one, which is leading the voltage V. But if IL was greater than IC in the other case, definitely this would have been in the lower direction, then the theta will be in the clockwise direction, and then my resultant was the lagging case where my total current I would have lagged the voltage V. So that depends upon these values. So this is my phasor diagram for the RLC parallel circuit in the case of the currents, or I can also call it as the current triangle. Okay, I will draw current triangle separately. Any doubts related to this phasor diagram of RLC parallel circuit? Just let me know अगर कोई doubt है, otherwise I will move forward. चलो आगे. Okay, so now we will discuss these different triangles. First one is the current triangle. Now what is there in the current triangle? We have already drawn it, so it is easy for me. I will draw it like this. So we will have here IR. Here I will have IC minus IL, and the resultant is I, and the angle is theta. So from here I can say I will be equal to under the root of IR square plus IC minus IL whole square. This is simple Pythagoras theorem. And from here I can say that theta is equal to tangent inverse of, what is the value now? Perpendicular upon base. So perpendicular is IC minus IL, IC minus IL divided by IL. Now if the case is that IL is greater than IC, definitely it would have been in the lower side, and you will find here that this value will in the numerator can be written in the negative form, or simply minus of value will be there, which shows that it has in the negative side current value. So second one is my admittance triangle. Admittance triangle. In the admittance triangle, I will again take the reference as G. Then this positive side, if I am considering, then definitely it will be BC minus BL, and the resultant is Y, where Y is equal to under the root of G square plus BC minus BL, and theta is equal to tangent inverse of BC minus BL divided by G. Okay, and last one is my power triangle. Power triangle, the power across the resistor is denoted as P, which is equal to V square G. Power across the resultant of this capacitor and inductance, or simply you can say that it's V square into BC minus BL, which is denoted as QC minus QL, right? And the resultant of these two will be S, which is equal to V square Y. This angle is theta. So I can write here that S is equal to under the root of V square plus QC minus QL, right? And theta will be equal to tangent inverse of QC minus QL divided by P. So these are three different parallel circuits, that is RL, RC and the RLC, and these are the phasor diagrams along with the admittance equations for this.